Okay, we've got an Lcr circuit here, which is what we'll always have for resonance. 200 microfarad capacitor, 100 ohm resistor, and 3 Henry inductor. So let's have a look at this circuit. Here's our circuit here. 12 volts RMS, alternating current, 10 hertz. We've got our capacitor here, and we're given the capacitance and the capacitive reactance. We're given the resistance of the resistor, and here is the inductor with its inductance and its reactance. So remember, impedance is reactance, and there's the two reactants, the capacitive reactance, the resistance of flow of current through the capacitor, and it's the inductive reactance. So impedance includes those reactants, those two reactances, plus the resistance of the resistor. So that's the total, and remember, we can't just add because we need to add the phases. So let's get back to where we were and do this. The space provided alongside, draw an impedance diagram and use it to calculate the total impedance of the circuit. So that should be pretty straightforward. Our diagrams, remember, tend to be a bit like this. Inductive reactance, capacitive reactance, and resistance. 90 degrees. So let's draw this. We're given that the inductive reactance is 190, and again, impedance is in ohms, and the capacitive reactance is 80 ohm, and the resistance is 100 ohm resistance. So remember, the inductive reactance leads the resistance by 90 degrees, the phase difference, and the phase difference between the resistance and the capacitive reactance is a further 90 degrees. So all we need to do is to find the total impedance is solve this. So let's do that. We've got 190 up and 80 down, so that together is 110 upwards, 110 ohms, so that there is the XL minus XC. So that will be 110 ohm, that will be the sum of the reactances in the circuit. But in order to find the impedance, we need to then combine it with the resistances. So let's just do this, our phasor diagram, and here there is the representation of the impedance Z. Impedance Z, and we can solve that using Pythagoras. So we can say Z is equal to the square root of 110 squared plus 100 squared, which should be 148, two significant figures, 150 ohm. Now calculate the RMS current in the circuit. Let's have a look again at our equations. We've got this equation here where we've got the voltage, and that'll be the supply voltage, is equal to the current in the circuit times the impedance. So let's come back. The voltage is equal to the current times the impedance, so that will give us the current is equal to the voltage divided by the impedance. The voltage is 12 volts, and the impedance we've just calculated there is 150, but remember 150 was a rounding, so let's use the actual value, or the nearer value. We've got 12 over 148, which equals 0.081 amp. 0.81 amp. Okay, calculate the phase difference between the supply voltage and the current. Now, our diagram that we've got over here is with the reactance and resistance, but it's the same phase as the voltages, because we will say that the reactance is equal to V over inductor divided by I. The resistance, of course, is V over I, and the capacitive reactance is also V capacitance over I. So if we cancel the I's out in each case, we'll end up with the voltage, VR, VL, and VC. So the phase difference is going to be this angle that we identified already between the supply voltage and the current. This is our angle. And remember, the current is in phase with the voltage over the resistor, because there's no capacitive or inductive effect in the resistance. So let's then use this. We can say, therefore, tan theta is equal to, tangent of theta is equal to 110 over 100, which gives us theta is equal to 48 degrees, and we will say the voltage, the supply voltage leads the voltage over the resistance by 48 degrees, which is the same as saying the supply voltage leads the current by 48 degrees, because, as we say before, the current is in phase with the voltage across the resistor. And calculate the frequency at which the circuit would resonate. Remember, at resonant frequency, the inductive reactance is equal to the capacitive reactance, a situation where the overall impedance is the same as only the resistance. So that means the resistance is the least at resonance, in which case Ohm's law, the current will be greater. So frequency there leads us to the equation which you've seen before, F0 equals 1 divided by 2 pi square root LC. So substituting in our values, which I'm going to gloss over, is equal to 6.5 hertz. Okay, calculate the current at resonance. Current at resonance, because XC equals XL, the impedance of the circuit, equals the resistance R. Because remember, if we have our phasor diagram, and we've got XL up here and XC down here, and resistance here, when XL equals XC, they cancel one another out, and we're simply left with the impedance equals the resistance. So the impedance of the circuit is R, so the impedance equals R, which was 100 ohm, and the current is equal to, we're trying to find current, voltage is equal to 12 volt, and we simply use the AC version of Ohm's law, which will give us the current is equal to the voltage over the impedance other way, equals voltage 12 over 100 is equal to a current of 0.12 amp. And explain why the current is maximum at resonance. At resonance, XC equals XL. So again, looking at our phasor diagram, trying to find the impedance Z, R, XL, XC. XL and XC are the same, so they cancel one another out. So we're actually left with resistance R. So the impedance at resonance, the overall impedance is only equal to R. That's the smallest impedance possible. And again, from Ohm's law, current equals voltage over impedance. If the impedance Z is small, current is large. And that is how we tune in our radio stations. When we have resonance at a certain frequency, we get maximum current, which tunes us into that particular channel.